Good morning, everybody. Everybody in the back hear me okay? Great, awesome. Well, thanks everybody for coming to actually session number 1 after the opening session. That was quite a challenge to top that first panel session. But my name's Joe Applegate. I am a senior principal hydrogeologist with Geosyntec up in Tallahassee. Been coming to PFAS conference every year since it was formed back in 2020. I was going to start with a little humor with a PFAS joke, but you know, PFAS is not a joking matter, and I was really afraid my PFAS joke just wouldn't stick. I know, we're sliding downhill real fast, so anyway. Jorge has mentioned that PFAS was first introduced at a conference in Marco Island back in 2019, and I was actually giving a PFAS site assessment tools presentation on a panel of various PFAS topics with the DEP. And my first question was, how many people in the audience, and it was about 150 people, have heard the word PFAS? And only about 30% raised their hand. And I know environmentally, we've all heard of PFAS now, but I was curious of the Americans across the nation, how many people have heard of PFAS in 2024? So according to a November 2023 study by Texas A&M AgriLife scientists, still only about 45.1% of Americans have ever heard of PFAS. 32% have heard of PFAS, but don't know what it is really. 10% know their community has been exposed to PFAS, but 98% don't believe their drinking water has been impacted by PFAS. So, 98% don't see it's a problem in their backyard. EPA has documented at least 8,200 PFAS sources across the country, and I'm sure that's going to increase by 100-fold by the time we're all done with it. But I do believe the pause we had in Florida the past 3 years with the Florida legislation has given time for us to catch up with the science of PFAS. Over the past 3 to 5 years, there's been a lot of activity with PFAS assessments at the federal, state, local, municipal levels, private levels. So we've learned how to assess it, and we're still assessing. We're in the 3rd and 4th phases of vertical and horizontal delineation of PFAS, and we're starting to do a lot of treatment as well. So I think there has been a lot of progress over the past 3 to 5 years, despite winter is here. I think we could actually use a little more time to catch up, because the more we learn, the more questions we have. One question in Florida is, are we delineating to 70, or are we delineating to 4? It's quite uncertain at DEP. We've been told to continue with the provisional numbers until the new MCLs are ratified, but I would expect that eventually we're probably going to have to get to 4 or less. And so people should be planning for that eventual outcome. It's probably going to be a year or two before DEP formally adopts and ratifies those new MCLs. And then there's the EPA regional screening levels that just came out there in the part per quadrillion. So I'm hoping our panelists can talk a little bit more about the analytical methods out there and the challenges we have just to get to the new MCLs versus below a part per trillion. Don't know if that's even possible with our tools these days. So with that, I'm going to start our panel discussion. We're going to save questions till the end. Each presenter is going to talk for 20, 25 minutes, so please write your questions down and we'll go over those at the end. Appreciate everybody being here. Our first talk is PFAS analytical methods and sampling techniques. J.P. Verheul with National Technical Sales, PFAS, and Ultratrace with Enthalpy Analytical. And we're really happy to have J.P. here.
Thank you. Good morning, everybody. That first panel was phenomenal, so thanks to everybody who presented and stood up here. It was great information and really sort of set the stage for some other wonderful talks today. I think my info is in the bio, so I won't let you look at my big head for too long. But I am J.P. Verheul with Enthalpy Analytical. If you're not familiar with Enthalpy Analytical, we're a network of laboratories across the country that focus on analysis of environmental samples for all sorts of things, including what I call traditional chemistry, organics, and metals. We do industrial hygiene work, we do emissions testing, ambient air monitoring, petroleum work, aquatic toxicity, and of course, PFAS. So on this map, we've got 2 Department of Defense accredited PFAS laboratories in our network. One located in El Dorado Hills, California, which is one of the first labs in the U.S. to develop the PFAS methods in the mid-2000s, and then a lab in Wilmington, North Carolina, sort of in the hotbed of Gen X. We've only got about 20 to 25 minutes today, and I was asked to talk about analytical methods and sampling techniques, which is a pretty broad set of topics, right? So what I thought I'd do is put a list here of some of most of the methods that are out there right now that most labs are doing, and then focus on what I think are the most relevant. And so while we're getting started, can I get a show of hands? Who here is with a drinking water utility, like an operator or drinking water? Anybody? Some hands. How about wastewater? Okay, good. Engineering consulting firms? Nice. Okay, so this may be known for some of you. How about litigation law firms, things like that? And got a few. And then regulators, finally. Okay. Anybody just hate it when somebody asks you to raise your hand when you're part of a group? All right, so what I think we're going to talk about mainly is, like I said, the most relevant methods, the drinking water methods, and then I want to focus on method 1633. There are other methods out there, non-targeted methods like total organic fluorine, total oxidizable precursors. We've got some ultra short chain and direct inject methods. If there's time during questions, we can go through it. And I've also got a poster for direct inject analysis, which is kind of a rapid turnaround time option that offers some lower quantitation limits and is really good for things like treatment technology. So if you're interested, come see me at the Enthalpy booth at the back of the hallway or come to the poster session. All right, so enough shameless propaganda. We'll get into the meat of this. We've got 2 drinking water methods EPA 537.1 and method 533. 537.1 is an older method, came out in around 2014. 533 came out around 2018. Both of these are used in the UCMR 5, Unregulated Contaminant Monitoring Rule number 5. What's interesting is that method 533, although it's a more expanded list, does not include all of the same compounds in 537.1. There were 4 compounds highlighted here in blue that showed a better recovery with that earlier method 537.1. And I think we heard earlier this morning that if you're participating in UCMR 5, what that means is your laboratory is having to process your samples by both of these methods in order to generate all of the necessary data to report to the EPA. And as a point of note, I'm happy to share these slides. So if anybody's interested in the slide deck, let me know afterwards and I'm happy to send it to you. Okay. So digging a little deeper on 537.1, that first method that came out, this came out after UCMR 3 identified that there were PFAS in drinking water systems. The EPA developed this method, rolled it out. It's got some unique QC requirements, so it requires a field blank collected with your samples as well as matrix spike and duplicate. And it has a 14-day holding time. Now, one of the things that is interesting about 537.1 is it does not use something called isotope dilution, which is sort of the gold standard for PFAS QC. And we're going to dive into that a little bit more as we move along. And it was great. It's the first method we had. It's wonderful, but it's not perfect. It doesn't do a great job with all compounds like PFBS. So the EPA developed a newer method, method 533. It came out a few years ago. Again, a longer list of compounds, includes Gen X, right? It does use isotope dilution, which is great. Like 537.1, uses a field blank and requires matrix spike and duplicate. It has a 28-day holding time, which is phenomenal. One thing I glossed over with 537.1 is, go back to the slide real quick, that 14-day holding time. When you're submitting a sample with a field blank, we, as a laboratory, would get a lot of requests from folks to, hey, hold that field blank. We may not want to run that until we know what the data from our sample is. But oftentimes, because this test is a little difficult to run, that data may not be available until the field blank is out of holding time. So having a 28-day holding time in method 533 is pretty critical. There are some extra QC parameters here, so it's important for the laboratory to process these as quickly as they get them in so that you can avoid any kind of turnaround time or holding time issues. Okay, so analytical chemistry is not the most fun thing ever. If you guys check out, I don't blame you, but if you remember just one thing from this talk, I hope you'll remember that isotope dilution is the gold standard for QA/QC when it comes to PFAS. And I want to explain a little bit about how it works. And so when we talk about isotopes, what we're talking about is different atoms of the same type of element that vary with mass based on the number of neutrons they have. So for carbon, for example, carbon-12, which is the most abundant form of carbon on Earth, 99% of all carbon is carbon-12, you have 6 protons and 6 neutrons, right? 6 and 6 is 12. 1% roughly of all carbon on Earth is carbon-13, 6 protons, 7 neutrons, right? So it's just a little bit heavier. There's also carbon-14, there's very little of it, it's unstable, we don't care about it right now. All right, why do we care about any of this? Well, that difference in mass between carbon-12 and carbon-13 is really powerful. It's something that we can leverage in the laboratory when we look at doing analysis. So what you see here are 2 structures, both of which are PFOS. PFOS is one of the 2 compounds that is listed in CERCLA, right? It's one of the oldest PFAS compounds out there. Now, these are not the same molecule. They're structurally the same, empirically the same. The biggest difference here is that laser pointer. Those 2 carbons right there with the yellow dots are carbon-13. They're isotopically labeled, right? And what this means is that the PFOS compound on the right is just a little bit heavier than the PFOS compound on the left. This is important because in the laboratory, these 2 compounds, these 2 PFAS molecules will behave exactly the same throughout the analytical process except when it comes to detection. We can differentiate them when we look at the chromatogram. What that means is that we expect the same behavior for both. So we can actually add some of the isotopically labeled PFOS to the sample before we start the analysis and then evaluate its recovery. And based on its recovery, we can tell a lot about the actual recovery of the target analyte that we're looking at in an unknown sample. And so here's a flow chart that sort of demonstrates that, right? So I'd say, for example, we get a sample that has an unknown concentration of PFOS. It's 100 nanograms, but lab, we don't know that. What we do is we will add 2 nanograms of that carbon-13 radioisotopically labeled standard to the sample, and then we'll take it through the process, right? Like we will extract it, we will clean it up, we'll concentrate it, we'll analyze it, and then we'll look at the data. And when we look at the data, we'll say, okay, what do we see for PFOS? We got 25 nanograms of PFOS in our data. Okay, that's what's in the sample. Well, hold on. We've only got 0.5 nanograms of our carbon-13 PFOS. We started with 2, and we ended up with 0.5. That means we saw a 4-fold reduction in carbon-13 PFOS, right? And because carbon-13 and carbon-12 PFOS will behave the same way, we can say, well, we're seeing suppression for PFOS in our client sample. It's not 25, it's actually 100, because 25 times 4 is 100. So that's isotope dilution at a high level, guys. It is extremely powerful. It is written into method 533. It is the gold standard. If you're working with your lab to figure out what methods you're using or what data you're looking at, that's an important part of the conversation. So what does that mean for previous data, right? Again, 537.1 was the only method for a long time. We do know a lot of folks that have tons of data that they started collecting before 533 came out. Maybe they go back and retest. So this is a data set from a real-world sample that we analyzed according to both methods. And you can see for most compounds, we're getting similar results across both methods, with the exception of this one right here, PFHXA. So by that 537 method, it comes out around 36 parts per trillion, but with 533, we're at 69. That's almost a twofold difference, right? So it's important when you're looking at historical data to consider the method that was used, and if you're comparing that with newer data that's being generated now, to look at what method are we using now, and are any differences we're seeing, maybe differences on the method, or are we seeing actual changes at our site or at our conditions? Okay, that's drinking water. So want to talk a little bit about this other method, EPA 1633, which covers groundwater, wastewater, soil, sediment, biosolids, tissue. Very powerful method. Anybody here familiar with 1633? Again, I love hands. Fantastic. Okay, so some or many of you may be familiar with the way this came about. So before this method came out, we only had drinking water methods, right? So as a laboratory, when we had consultants or other folks come up to us and say, hey, I really want to know if there's PFAS in my groundwater or in my soil, we didn't have a method, right? We could say, well, we can modify one of your drinking water methods for you, and we'll run it by this modified method, but that's what our lab does, right? And so every lab had sort of their own unique modified method. At Enthalpy, we call ours isotope dilution. Other labs call it 537 modified. Well, 1633 changed all that. So in August of 2021, the EPA issued a draft method, 1633, and they said, great news, guys. We have this method out. It's going to be for all these other matrices. It's drafted. We would love your comments. Also, start using it right now, which is bananas. But we did, right? There were 4 drafts that came out over the following years, and then on the last day of January this year, we received the final version of this method, right? So it has gone through multi-lab validation. It is standardized. This will be the method that is used for pretty much all non-potable matrices moving forward. And I want to talk a little bit about the details of it. So now that we have it, what are the implications? Well, we heard a little bit already this morning about it, right? We know that PFAS is being written into NPDES permits. It is established in RCRA. It is in CERCLA. 1633 is going to be the method that is going to be used for most of these projects, right? Like method 533, it is liquid chromatography, mass spectrometry, uses solid phase extraction with a weak anion exchange column, and isotope dilution, right? So we've got that gold standard, which is phenomenal, and a boatload of quality control. There's some things that 1633 does really well, right? So when we talk about PFAS structures, we talk about branched and linear isomers, right? These, again, are both PFOS, technically, right? But this one here is linear. This one here has that little branch right there. So the same molecule, or the same compound, right, but different analytical structures, or different structures that show up analytically in different ways, like this. So older methods might only require you to quantify the linear PFAS right there, right? That linear PFAS is that large peak. 1633 does a really good job of integrating these smaller humps right here, which are your branched isomers, right? So when you're talking about total PFOS, you're looking at the linear and the branch combined, it's important, right? We're not looking at suppressed data. One of the other things that 1633 does well is encourage larger fragmentation patterns. So when we talk about mass spectrometry, or the way we analyze PFAS, at a high level, kind of goes like this. You take your sample after you've extracted it and concentrated, and you introduce it into the LC-MS. In the liquid chromatography column, all those different PFAS molecules separate out, and they come out of the column at different times into a mass spectrometer, which then ionizes or explodes the sample into little fragments, like you see here. And then those go on to another mass spectrometer, which evaluates the mass-to-charge ratio of each of those fragments as a function of the time that they come out of that column, right? So the more fragments you have, right, the higher level of precision or confidence you can have in the data that you're generating. So important stuff here. Holding times make sense for 1633, which is fantastic. You've got 90 days in water, soil, and tissue. You've got 28 days if you freeze it. Sorry, you've got 28 days in water if you refrigerate it. Still 90 days in solids and tissues. Now, there are some caveats here. There are some compounds that will degrade quickly and do need to be analyzed right away. Those are listed here. They're also outside the list of 40 compounds included in 1633, so by and large not something you need to worry about unless you know you're targeting it. Now, it's a great method. Doesn't necessarily mean it's a method that you always have to select, right? Depending on the scope of your project and what you're looking to do. So I thought it'd be helpful to highlight some of the key differences between, for enthalpy, 1633 and our internally developed method, which we call isotope dilution, right? So maybe you want to look at a larger list of compounds than just the 40 in 1633. You may, sorry guys, trigger happy. You may want to look at a longer list. You can use that isotope dilution method. Or maybe you're working at a site where you have extremely limited volume, a well that doesn't purge or doesn't recharge quickly, or you're doing a treatment technology pilot study and you have limited volume, then isotope dilution may make more sense. So this is something that your laboratory can help you figure out, right? I guess the take-home message is that 1633 is great. We are going to see it applied for a ton of stuff. It may not always be the best method for your applications. Okay, it's challenging, right? It has got a ton of QC, guys. I mean, there's another slide I did not include here, but I think for every one sample that we run, or every batch that we run, there's approximately 10 to 12 quality control samples that have to be run alongside with it. This means that it takes forever to run, and it is more expensive. There are some restrictive criteria in terms of how we manage dilutions. If we have to dilute the sample above a certain threshold, then the lab has to go back to the very beginning and perform the solid phase extraction process all over again, and I can tell you that is an extremely lengthy process. There are a lot of labs that have been suffering extended holding times, or sorry, turnaround times over the last few months. It's a big part of why you got to go back and re-extract these things. There are some non-standard QC acceptance criteria that we have to look at. So we mentioned tissue, right? There's something called a bile salt interference check. So when we're calibrating our instrument and doing all of our QC, we have to look for a compound called TDCA, which behaves similar to PFOS, and show 60 seconds of difference between those peaks. It's hard to show that on a lab report without including a bunch of raw data. So some reporting challenges. And then we need a ton of sample. I mean, when you're sampling, you're looking at close to half a liter of sample for each, and that's collected in duplicate, plus a little bit extra, and especially if you need field blanks or matrix spikes in duplicates. If you need the lab to archive it, they're gonna have a tough time storing it. So not the easiest thing. All right, and in the remaining minutes, I do want to talk about some sampling techniques, right? Sort of best practices for those of you that may be new to this, or some consultants who are looking at doing this soon. So PFAS is everywhere. It's all over the place. Contamination is ubiquitous. This is one of the hardest parts about sampling, right? And we worry about it in the laboratory. So when we're in the lab, these are some of the common sources of contamination we deal with. As a laboratory, we're working constantly with our vendors to lot check new supplies, new reagents to guard against contamination. So it's worth knowing that, this can happen in the laboratory, and these are some of the sources. When you're collecting, what you wear really matters, right? We know that PFAS can be in sunscreens, it can be in skin lotions, perfumes, it can be in makeup, it's in clothing, right? You're wearing waterproof or dry fit clothing, so you want to avoid all of that, right? Cotton clothing is the way to go. You want to avoid a lot of those products. I think it's Michigan's EGLE, their regulatory body, has a list that they update routinely that includes some of these products that they know are PFAS free. So if you're looking to go sample, they may have some items that you can deploy in the field that are PFAS free. And don't eat out there, right? Food packaging has PFAS all over it, so good practices. I don't know that it's on here, but no latex gloves, acrylonitrile gloves only. So before you sample, work with your laboratory. Understanding exactly what you want to collect, what your timeline in, will help inform what that collection process looks like in terms of what the lab's going to provide you for the correct containers, as well as any PFAS-free water you may need for field blanks, trip blanks, and things like that, as well as your report type. Okay, so chances are you're going to need to decontaminate. You'll want to do this with PFAS-free water, which you probably can get from your laboratory, or if you create your own water, you could probably send it into the lab to have them check it for you. You also may want to use some kind of detergent, a non-PFAS detergent like Alkanox or Liquinox, which is phosphate-based. For folks in the water industry or even wastewater, if you've got your own labs or if you're a consultant going into a lab, I spent 10 years as a chemist, so this picture is hilarious to me. Keep an eye out for what's going on in the laboratories. You know, this is somebody collecting from a local lab some water for PFAS testing, and right here, this is a deionized water tap with a big old piece of Teflon tubing sticking off of it, right? So when you're out there collecting, keep an eye out for potential sources of contamination that you can maybe avoid, right? For grab samples, you know, this is wastewater treatment plant right here. Stainless steel dipper is great. Again, decontaminate it. There's a part number if you need it. Decontaminate it like we talked about with PFAS-free water and that PFAS-free detergent. We say waste twice and then collect once. Use your ballpoint pen and collect everything in duplicate. Can't stress that enough. For soils and sediments, stainless steel is the key, right? So you can use augers or shovels or spoons as long as they are stainless steel and not coated. Again, decontamination, right? You're going to use that water and that detergent. And then if you need to do a composite sample, right, put it in a stainless steel bowl, homogenize it, and then subsample that and send it into the laboratory. Obviously, avoid as much contact as you can with things like Teflon in the process. Okay, and when you're ready to send this into the laboratory, it'll be much like sending in samples that you've sent into other laboratories, right? Line the cooler with a trash bag, put your samples in Ziploc bags, wet ice, do not use dry ice, do not use blue ice, tie everything up as tightly as you can, and then ship it on off. Make copies of your chain of custody. The laboratory will most likely provide everything that you need, but that's a good conversation to have up front when you're ordering containers. Okay, and then fun lesson that we learned. So these are two samples that were collected by a wastewater utility from a raw influent point, right? So we had a utility that collected every Monday. They went out and collected samples coming into their wastewater treatment plant, and every Monday they looked like this right here until one Monday when an operator was sick, couldn't come in, came in on a Thursday and went to go pull his weekly samples, and it looked like this. Turns out, Thursday is the day that the dye manufacturer up the river discharged, right? So when you're looking at collecting from industrial dischargers, you want to be mindful of the schedule that you're looking at, switch it up, right? Understand when your dischargers are actually going to release and sample accordingly, right? And then one other thing that's worth noting is that we can add analytes. So if you do have certain industries that are known to produce PFAS, maybe they're looking at reporting for TSCA or TRI, and those are not included in any of the standard list, it may be that the laboratory can develop the methods further to test for those. We do a lot of that for big industries. Okay, so again, lots of different methods out there. I really just kind of scratched the surface at a high level for some of the most relevant ones. Got a couple minutes left here, so we'll just sort of speak on these, and then if we want to talk about it during questions or afterwards, please come find me. I'll talk about this stuff all day long, guys. But we heard this morning about this AOF-CIC, adsorbable organic fluorine, non-targeted method that's going to be used to kind of approximate, right, the total PFAS load coming in. Really powerful stuff for wastewater treatment plants that may need to evaluate what they need to treat for, right? I think it was Taryn that said earlier, most labs tap out around 100 compounds, right? PFAS is like 15,000 at this point, I think, depending on how you classify it. So AOF is a powerful tool. Similarly, we've got total oxidizable precursors, which is a great way of measuring compounds that may form terminal PFAS, right? So these can be biodegradation products of PFAS that are discharged that will change in the environment and may not show up in our targeted analyses. We've got some ultra short chain methods out there. So all of the methods we've talked about right now are really only good for compounds that are about 4 to 5 carbons up to maybe 18, right? The C1, C2, C3 compounds will not show up in those methods, right? And those smaller chains are used to create or synthesize PFAS at the industrial level, right? So there's no established EPA method for those yet, but many labs have developed it, and that is something that I think is probably coming. We didn't talk much about air. I know there were some questions earlier and yesterday about air. There are air methods. It was mentioned earlier that those methods were designed to evaluate the treatment or the products of incomplete combustion from stack emissions, right? So that would be OTM 45 and OTM 50 right here. Those are stack methods. Now, we have seen folks that have looked at augmenting those for other applications like vapor intrusion and ambient air, but right now that is sort of where the market is going, or where the industry is going when it comes to air methods. There are some other methods that folks are looking at modifying for air, like TO17 method, sorbent tube, but these are the only two EPA methods that exist right now. I think that's it, guys. So, Joe, thank you.
Perfect, thank you. You know, I've heard that's twice now, 15,000, we're up to 15,000. I think I heard at the remediation conference because of the definition changing to anything that has a carbon fluorine bond, it was up around 22,000. That's just what I heard another presenter give. But anyway, lots and lots of PFAS compounds. Next up, we have Dr. Amanda Miller. She's an analytical and research scientist with NCASI. And she's going to talk about application of proposed EPA PFAS methods for wastewater. Thank you so much, Dr. Miller.
Thank you. It's so nice to see everyone here. It's nice to see such a big crowd. I'm really excited to be able to talk about our research study that we were able to conduct at NCASI. Me and my colleagues worked really hard on this together, and I'm really excited for the opportunity to talk to you guys about this. I want to just acknowledge my colleagues that worked on this project with me, Dr. Varuna Karadina, Cher Lindelin, and Dr. Giff Johnson. At NCASI, we are a nonprofit that works for the pulp and paper industry. So we're trying to look into research topics that are really at a forefront for our industry and try to give our members the best reliable information that they can get. So our big key findings for this research project were that improper sample handling can cause issues. Sorry, let me move this. Can cause issues. This can stem from mishandling the samples and extract dilutions, and which can artificially inflate reporting limits, leading to non-detects. This is mostly because 1633 is a performance-based method. So because it's a performance-based method, the certified labs have the freedom to handle stuff like suspended solids in ways that they see best fit with their professional judgment. Reporting limits can differ amongst labs. Just because you're using 1633 doesn't mean that each laboratory can get down to as low of a detection limit as another laboratory. So it's really important to keep that in mind when you're choosing a laboratory based on your project needs. Specifically for our members, we're worried with NPDES permitting limits and everything, so we want to make sure that they're choosing certified labs that have minimum detection limits at or below their limit. And we also looked at both EPA method 1633 and 537M, and they're both very different. EPA 1633 stands out as a more robust method, offering lower detection limits and a broader range of analytes compared to 537M. So I want to just describe how our study took place. So our key objective was to determine interlab variability in PFAS concentration detections at these EPA accredited labs. So we contacted 5 certified labs to have our sample tested by their facilities, and we wanted to see if these same 5 labs got the same results and the same hits between lab and lab, because they've all got the same samples. And we wanted to identify any differences in PFAS measured using 1633 and 537M. So our approach was, we took a very in-depth approach. We learned a lot about these data packages right when we sent out our samples. So we requested level 4 data, which level 4 data packages, I'm not sure if many of you are familiar with, but they can be about 4,000 pages, and you're looking at basically every graph of raw data that the laboratory produced. We also looked at their sample handling protocols and their QA and QC to determine their reporting biases and other complexities related to our industrial matrices. So we also reported our findings in normalized relative concentration, and this indicates the relative concentration differences among the labs. So basically what it means is that we're looking at the target concentration of the analyte and dividing it by the total average sum of the total PFAS detected. So for our study, we used two different sources for our samples. For our sample sets, we have source A, which was from a single facility where we are looking at their intake, influent, and effluent. What's interesting about this facility is that your TSS values, or your total suspended solids, was between 10 to 36 milligrams per liter. And what's really interesting about 1633 is that you cannot pass more than 50 milligrams of solid through the SPE cartridge for the extraction protocol. So that's really important to keep in mind when you look at source B. And source B is actually a composite sample from 3 mils, and it looks at an influent, but our TSS value in our influent is extremely high. It's what we would classify almost as a worst case scenario at 1,500 milligrams per liter. And then our effluent that we were looking at for source B has a TSS value of approximately 42. So a brief overview of 1633, the US EPA published Method 1633 in January 2024 and was finalized for analysis of 40 PFAS compounds. The matrices that this method addressed are aqueous, which includes wastewater, groundwater, and surface water, solids, and tissue matrices. Depending on the state, the NPDES permitting may allow the application of Method 1633 and/or another laboratory-based method known as 537M modified for PFAS analysis in wastewater. However, once promulgated, 1633 is going to be what's going to be required for regulations. So I want to first start off by looking at some of our data. So this first graph is showing our influence sample from our source B. So remember that influence sample has really high number of solids. And what you may be asking yourself is, why are all the detections different? Why doesn't it just look the same across the board? And that's because each of these labs had the flexibility and the freedom to use their professional judgment for how they wanted to handle that high amount of solids. So the first lab, Lab 1, which is shown in blue, took an aliquot of 25 milliliters of that sample. And then they also ended up having to dilute the extract, which, because they did the aliquot and dilution, that artificially inflates their reporting limits. So they're not seeing those low concentrations of those analytes that are at their detection limits because they're artificially inflating their reporting limit. What was really interesting about Lab 1 is that they show that they have a really high hit for PFBA. But what's interesting about this analyte is this analyte was not observed in any of the other 5 labs, which is why we were led to believe upon looking at the data that it could likely be a false positive. That's because PFBA is one of a few of the analytes that doesn't have a conformation ion. So majority of how this detection works is you have 2 ions that you're using to detect the identity of this compound. But for PFBA, you only have 1. So it usually tends to be a tricky analyte for a lot of these laboratories. Next, I want to talk about Lab 2, and as you can see, Lab 2 has many non-detects compared to Labs 3 and 5. That's again because Lab 2 decided to do a 5 times dilution of the sample and an extract dilution, again, which artificially inflated their reporting limits. Lab 3 is what we would refer to as our gold standard. They were able to pass through the entire 500 milliliter sample through the cartridge. Upon contacting the lab, we found out that it was likely that they used centrifugation to be able to separate those solids, which is allowed by the method. And as you can see here, because they were able to do that and they ran an undiluted extract, you were able to see a lot of these other analytes that we weren't able to see in other laboratories. Next, we have Lab 4. And Lab 4 went right off the bat, was able to extract the entire 500 milliliters of the sample. But because our substance, our wastewater, is very pigmented in color because of a lot of lignin and tannins, they went straight ahead and diluted the extract 10 times, which again artificially inflates the reporting limits. So you're going to have all these non-detects with really high reporting limits. And then Lab 5 was an interesting laboratory. They also followed the EPA's best practices, but once they noticed that our solids count was extremely high, instead of passing the entire 500 milliliters of the sample through the cartridge, they opted to use their professional judgment and use the 125 milliliter bottle that was filled for TSS analysis. So they extracted essentially a smaller volume of sample. And as you can see, they have comparable results to Lab 3. Now we're going to move on to the effluent of source B. So the effluent of source B was right at the cusp of being almost over the limit for solids numbers. So the effluent here again was 42 milligrams per liter, and because of that, these labs also used their professional judgment to see what would work best for their laboratory scenario. And Lab 2 again had to dilute the sample right out the bat, but they were able to run an undiluted extract. So that's why they have some similar comparable hits to the other laboratories. And Lab 4 was able to pass through the entire 500 milliliters of the sample, but the extract was diluted 10 times. So those reporting limits were greatly increased. Next, I want to move on to our source A. And our source A, with this sample, each laboratory was able to extract the full 500 milliliters. But what's interesting is why aren't they getting all the same hits then? And that's because each laboratory has their own set reporting limits. So as you can see here, Lab 2 has a lot fewer detections than Lab 3 or Lab 1. And that's because when we compared their SOPs, their reporting limits are higher. So because they already have higher and elevated reporting limits, it's hard for them to get detections of our lower analytes in the sample. This was also observed in the effluent again, but again, because of that lower TSS value, you can see that there's less variability. So the biggest thing, other than reporting limits being high, is that the TSS has a great effect in what's going to be detected, because the way these labs handle total suspended solids can vary. So we also wanted to compare the data between 537M and 1633 data. So we sent that same sample out and got it analyzed both by 1633 and 537M. And so what you see here is that the solid colors are all conducted with 1633, and then the checkered colors are what was detected with 537M. And what was interesting and what we saw is that when you use 1633, you're going to get a lot more detections. And that's because 1633 has lower detection limits. So you might be seeing some of the analytes that you haven't seen before. Also, 1633 has more analytes that it's looking for as opposed to 537M. 1633 has the total list of 40 analytes, and 537M varies between lab to lab because it's a laboratory method. Again, here we're looking at the effluent, and you see the similar pattern in results that with 1633, you're going to get more detections of these analytes, but they usually tend to be at lower concentrations. Again, that's because these detection limits now are lower, so you can see the lower range. So just to highlight our key findings again is that improper sample handling can cause a major issue. And that's one thing that we have to be aware of in our industry, because we're dealing with pulp and paper wastewater. There's a lot of solids, and mishandling these samples and extract dilutions can artificially inflate these reporting limits, leading to non-detects and unreliable results. And then reporting limits can differ amongst labs. Each laboratory has to go for their own rigorous certification protocols and their own rigorous detection limit determinations in order to become a certified lab. And some because of that, and because each laboratory uses different pieces of equipment, each laboratory has their own unique detection limits and reporting limits. So it's really important to request the reporting limits for a specific lab prior to starting your sampling process. This is to ensure consistent and accurate data that matches with the required NPDES limits. And then also EPA method 1633 and 537M are different. EPA 1633 stands out as a more robust method offering lower detection limits and a broader range of analytes. And then data quality evaluation is critical. And for us to see all this, we had to go through and analyze and check out level 4 data packages. If you're just looking at the normal level 2 data packages, you're not gonna see this in-depth of detail. You're not gonna be able to figure out some of the stuff that we were able to figure out. So it's vital. If you wanna see everything that the lab did, you have to request the level 4 data. And you have to go through it to ensure the reliable conclusions. And then here's my contact information. If you guys have any questions, please feel free to contact me. I'd be more than happy to answer. Thank you.
Thank you, Dr. Miller. 2 excellent presentations on laboratory analytical methods for PFAS. I know it's hard to keep up. It seems like there's new methods coming out all the time, so we really appreciate the specificity of those 2 presentations. Next, we're going to move on to Bryan Massa. Bryan's a licensed certified professional principal and regional manager for HRP Associates. He's going to be talking about confirmation of the sources of PFAS detected in municipal drinking water supply wells using several forensic lines of evidence. So, Bryan?
Thank you. Hello, everybody. So I'm going to present a case study that relied on multiple lines of forensics evidence. It also used isotope dilution, which is the gold standard for the testing. And I'll kind of give you a high-level review of what we did and kind of how we were able to differentiate multiple PFAS sources that were all impacting the municipal drinking water supply system. All right, so here's a little background on the area. So we've got a municipal airport right here. We've got drinking water wells down here. We've got locations where AFFF is stored, locations where AFFF is sprayed. We've got a county fire training academy where they train with AFFF. And we also have a municipal wastewater treatment plant. Now, the groundwater and hydrology in this area all goes down to these drinking water wells. So in 2013, 2014, during the UCRM study, PFAS was detected in these municipal drinking water wells. The regulatory agency kind of looked back, saw the proximity to the airport, and basically said that you guys are the source of the PFAS detections. So we got involved with this site, and we were first delineating the nature and extent of the impact. We wanted to find out the sources of PFAS, where they were, if there was a hydraulic connection from the airport to the drinking water supply wells, as well as what the background was in this area. As everyone has said before, PFAS is ubiquitous. It's in all sorts of materials. So there are background levels that are present that aren't the result of a deliberate release. So part of our investigation for the environmental forensics aspect, it was based on a pretty extensive groundwater sampling and analysis program. We used isotope dilution. We ran hundreds of soil samples, hundreds of groundwater samples. We also did a background study. So we needed to know what the concentration and what the exact PFAS analytes were that were coming onto the property. So we looked hydraulically up gradient to the airport. We looked hydraulically cross gradient, and we looked down gradient. We focused on interviewing airport staff to find out exactly what type of AFFF that they'd used. And then we did PFAS chemical signature analysis. So what we did was we had this very robust data set, and we normalized the data set. So the amount of PFAS analytes changed over time as the labs got more involved in new methods. But originally there was maybe 25 PFAS analytes originally. Now it's around 40 or so. So we did a normalization where we summed up all the PFAS analytes that were reported by the laboratory, and we called that total PFAS. And then we divided each individual analyte by that number to determine what the relative percentage was. So it gave us a quick way to look at the data to really hone in on, were there unregulated analytes, those that weren't necessarily regulated by the regulated community, that we're seeing to use for source decision purposes. So what this shows is about 6 years worth of investigation. So what we have here, again, this is a fire training academy. Groundwater flow is all kind of converging onto this area here. When we started the investigation, everywhere that we looked, we detected PFAS. Everywhere. I want to say that out of the 300 samples, there's probably less than 10 that didn't have a PFAS detection. So when we initially started looking at this, we weren't doing forensics yet, but we were seeing that there's PFAS up here. There's no hydraulic connection to the airport. There's PFAS over here. Again, no hydraulic connection. PFAS over here, which we determined is the airport source area. PFAS here. So we identified 4 plumes that were very distinct, had very different chemical signatures. There was a plume that was coming up this way, and it was going right down to the drinking water supply area. There was another plume up here from a fire training academy that was also going down to this area. Very distinct chemical signatures that were actually consistent, which would have been detected in the drinking water wells. Then the airport, which is shown by this plume right here, and then a small one over here, had a completely separate and different chemical signature. And that was based on the type of material in the firefighting foam that they had used. We wanted to find out if there was also other things that were contributing to this. We had a general idea that there's a fire training academy. Firefighting foam is a big known source. Wastewater treatment plant. So we looked out to see, was there a regional issue? It was atmospheric deposition playing into this. So we collected about 20 samples, from all over the area. Most of these samples were collected in, wooded areas. And we found PFAS detections in 19 of the 20 samples. 8 of the samples actually exceeded the regulatory standard when we had no known source. The potential sources of this, everyone's kind of covered those before. Aerial application of pesticides is a known PFAS source, atmospheric deposition, food packaging, littering, all kinds of other potential sources were found. So we started to look into, well, how can we prove that the detections that are being seen at this drinking water supply system aren't related to this municipal airport? It's clearly a different chemical signature. So we interviewed airport staff who had been working there for about since the 1980s, and they identified that they had always purchased a fluoropolymer-based foam. This is a mil-spec foam that has a very distinct signature, and it matched what we had been seeing. They had a predominant 6,2 fluoropolymer detection in their source locations. We looked back at purchase records. The airport had 20 years worth of purchase records showing that they had consistently purchased this same type of foam. This also matched ITRC's put out timelines for when these foams came into use, and fluoropolymer use was available in this time frame. So now I'm going to kind of get into the forensics and how we looked at this data set pretty quickly. So when we developed all of these ratios, we had 300 samples. We looked at soil, we looked at groundwater. And the way that we quickly did this was we plotted them. We made radar plots. So we could quickly look through the data set and see comparisons on what each signature looked like. So we did this for everything. So I could see what signature was coming onto the airport, what signature was leaving the airport, what signature was in the source areas, what signatures were detected in the municipal drinking water wells. So right here, this one right up at the top, this is the signature from the airport source area. It's 80+% 6,2 fluorotomer, which matches their purchase records and what the firefighters folk had indicated. Down here, you see, other PFAS analytes that are in there that are contaminants from the process making the foam, but they're in there. Then we decided to look at what was the signature at the Fire Training Academy. That site was also being investigated, but wasn't identified as the source because it was about 7,000 feet away. So when we started to look at their data, you can see it's completely different. They have a PFAS tail predominantly, so they're using the older type of firefighting foam. So then we said, well, let's compare what we see at the municipal drinking water well. So this right here is what the municipal drinking water well looks like. And you can see it's predominantly PFAS, but it does have some 6,2 fluorotomer in there. Again, this was the airport signature, and then you've got Fire Training Academy. The signatures are very, very consistent with each other. So then we looked at the other wells. So there's 3 wells that are kind of all clustered around each other. And we had traced the airport's plume to about 600 feet away from this drinking water well. And all of the analytical data was extremely consistent. You can see, the airport signature. Sorry. You can see the airport signature there, approaching these wells, but not there yet. So we figured that based on the groundwater hydrology of the area, that in about 2 years, the plume would make it there. And then in 2022, all of a sudden, you see this big spike of 6,2 fluorotomer in there, showing that now there's a commingled plume. Now, why this was important is that drinking water system had gone into effect in 2020 and was treating the water now. So this is the third drinking water well. And again, you can see is the airport signature. You have no detection of 6,2 fluorotomer. And then you see the Fire Training Academy signature. Again, very, very similar. So another thing that is important is how PFAS has fate and transport mechanisms associated with it, and it migrates differently in groundwater. So what this shows is retardation coefficients, and PFAS plume travels separately. So all these little lines here are different PFAS particles, and 6,2 fluorotomer is faster than the regulated analytes. So when we were tracking the airport's plume, you could track it based on the extent of 6,2 fluorotomer, and all of the other regulated contaminants would be behind it. So we had 3 lines of evidence. We had the forensic signatures that showed that 6,2 fluorotomer was the predominant contaminant. It wasn't detected in the drinking water wells until 2022. We had airport records that showed they had purchased this particular type of foam, and it wasn't consistent with what had been detected. So we collected samples and we sent them to Battelle. So Battelle has a special type of PFAS forensics analysis where they can look at the 40 that most people do, but then they have a list of around another 500 that are tentatively identified PFAS compounds. And they can run that, and they can do a hierarchy cluster, which is what this is right here. So when we sent them the samples, we sent the 3 drinking water samples, ME1, 2, and 3. And then we sent them 3 other samples that represented the airport, and they were also representative of the background area, and then what would be from the Fire Training Academy. And the report basically concluded that Marwell 1, 2, and 3 were more consistent with the Fire Training Academy than with the airport. So it was another line of evidence that supported this. So the groundwater travel time was important, and the proximity. So one of the things that makes PFAS interesting is it can stay in the surface soil for a very long time and can take a reasonable amount of time to get to depth. And the reason that the impacts from the fire training academy had occurred so quickly is that they sprayed into a pond. And when they sprayed it into a pond, it made it into the groundwater much, much quicker than when it was applied at the ground surface. So when we looked at the travel times, there's a grouping of drinking water wells that are right up here. And the fire training academy is quite close to those. So what we had determined is that the fire training academy had likely impacted these wells within about 6 years of them starting to apply AFFF. The fire training academy had gone into operation in the 1960s. AFFF is in the mid 1960s. So sometime late 1970s, early 1980s, the plume had reached it to this area and then had been circulated around the community. The community discharges to wastewater treatment plant that was shown up there, and then that water gets discharged to sand beds, which makes its way down this way. So our conceptual site model started to kind of point out that a release from up here had made it to these drinking water wells, which were circulated around town to over here, and that we had this first plume that was migrating down. Now, to get from here to here is 26 years. But again, the impacts occurring in the 1970s, sometime in the early 2000s, it made it down to this area. And at the same time, the plume from up here continued to go past these drinking water wells, migrate down here, and get down to this location. So the timeline that was critical on this was the fact that the foam had been sprayed into the pond. It took almost 20 years for the impacts up in this area to make it down 20 feet before it got to groundwater. And then when it moved with groundwater, it was moving at 300 feet per year, thereabouts. So it only took, 6 years to get down here. But, we were able to trace the signature here, 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 and here. And it matched up perfectly with our conceptual site model. So the fate and transport time of the 285 feet per year from when we first detected it, as we, watched it migrate after each year, to ultimately when it got there. So what this kind of shows now is removing everybody else's PFAS contaminants and looking specifically at the airport. So this was a very important part of the investigation because the regulatory requirement is to delineate the nature and extent of the PFAS plume related to the release. And if you just looked at the regulated PFAS analytes, there was no way to distinguish anybody's plume. There's PFAS everywhere. So what we had done is, because we knew 6,2-fluorotolymer was the faster moving analyte than the regulated analytes, we were able to track the plume and model it based on 6,2-fluorotolymer. So we knew what the concentrations were here, and we could watch it as it moved down here because the 6,2-fluorotolymer was extremely stable. There was no degradation to it, and you could watch it basically drop from dilution and dispersion as it migrated down here. And then by the time it gets to the drinking water supply wells that are over here, it has dropped down to below the regulatory standard, which at the time was 20. Again, this radar plot up here kind of shows in 2020, plume from the airport wasn't there yet. We had tracked the 6,2-fluorotolymer, this guy right here, to right about here. We had monitoring wells all over the place over here, and it wasn't there yet. So we presumed that within 2 years, we would see that spike. We continued to monitor, and we saw the plume progress. And then in 2022, we detected it there, and we had a commingled plume at that point. The modeling also showed that the airport's plume had no connection to the other 2 municipal drinking water wells that were located down here. And the conceptual site model shows that these guys were likely impacted from the plume from the fire training academy going to the wastewater plant and then ultimately migrating down there. And that's kind of how you got that cross-gradient plume that was showing up. Battel's signature tool was also a vital piece of this. It was the additional line of evidence that kind of correlated all this stuff together where we could look at it and say, okay, these radar plots are very simplistic. This is a much more in-depth analytical review that's looking far beyond the 40 that we were using during isotope dilution. So this study was critical for the airport because, one, they were initially identified as the source, and there would be future litigation associated with this. This was an impacted drinking water municipal supply that had been impacted with PFAS for probably 20 years before treatment went in place. Treatment went in place in 2020 at the cost of around $20 million. The municipality put that treatment in, and the airport's plume reached that area 2 years after treatment went in. And one of the solutions was compensation to the municipality for the construction of the plant to pay for their part of the contribution. But again, this work was all done in the very beginning with environmental forensics as kind of a way to look at the ubiquitous of PFAS, because it really is in everything. You see it in your stack emissions and insecticides and food wrappers. So to have a pretty robust data set and to look at beyond what your regulator may be looking is extremely important. You know, in Massachusetts, we regulate 6 PFAS analytes. EPA will have their 5. But if you only look at that group, this type of investigation is impossible. You need to look at a much larger data set to come up with these type of conclusions. That's it.
That's great.
Excellent presentation, Bryan. We'll open it up to Q&A right now. One I have for Bryan is, I didn't realize that Verheul would analyze your data. Do you actually send them samples, or do you send them the analytical data and they reduce it?
No, I'm not sure if this is on. I actually did send them samples. To just be clear, I used to work for Verheul a long time ago, so I knew I knew that the lab had some really good capabilities, and Verheul had a specialty lab in Duxbury, Massachusetts that these samples went to, and then they worked with their Columbus lab to do some of the additional testing on it. So it was very, very interesting stuff. This is a proprietary method that Verheul has, where the other part that I didn't even get into is if you don't know what your material is, they can plot it and say your sample is consistent with landfill leachate, it's consistent with AFFF, it's consistent with electroplating waste. So they've got this library of stuff that they have of known sources. They can give you these cluster plots that kind of show where you fall into. So our samples, of course, fall into the AFFF realm, which is what we expected. And then, again, it was very helpful.
But that was independent of the forensics you had already done, right?
Correct. I did all this forensic years before. So we collected those samples, I want to say, in 2022, right before the impacts had occurred at the municipal drinking water wells. So this was kind of the last piece. We had already kind of put the whole puzzle together and knew what our conceptual site model was and what we were seeing with the analytical, but I wanted something a little bit more solid than that, just knowing where this was going to go. So that's kind of when I talked to some of the folks at Verheul, and this testing was available, and it was something that they were using, so it made sense.
Excellent.
Hey, so I have a question for the last presenter. Really interesting case study. My two questions. The first one is, can you give me like an order of magnitude of like how much something like this costs? Because you have like groundwater modeling in here, you have a ton of PFAS testing, you have the specialized forensic testing, like order of magnitude like $100,000, $1 million to do something like that?
More into your second number.
Okay, yeah, because I'm thinking like for, you gotta like,
the samples are
the scope of the problem
expensive.
has to be something super serious if you're gonna do like $1
Yeah,
million worth of testing.
The other thing I didn't get into too is that a lot of these monitoring wells were clustered wells that were terming grouted, and this plume's over 100 feet thick. So this plume is very, very deep, and that's kind of from the recirculation aspect to it. So some of these monitoring wells are $15,000, $20,000 just to install, because of the depth and how they're clustered and terming grouted.
Yeah, and then kind of the follow-up question to that is very technical stuff. Does this, like when the rubber meets the road and you're going to court on stuff like this, does this type of information kind of go over the head of people, or has it been shown like this can actually impact court cases?
I think it's getting there. I've had to bring this topic up at many different discussions over time, and I think originally it was something that wasn't really used and people weren't really understanding what it was. This type of stuff people have been doing for 20 years with petroleum and age dating and kind of other things, and this was just a new way to look at the data and kind of present it. And I think I've seen over time that others are doing the same thing, similar type of stuff. But a lot of people now, even the regulators and municipalities, are kind of understanding this and saying, yes, we agree with this. And then the final piece was the Patel testing. That was kind of my additional line of evidence that now we've got high resolution analytical data that's going back to kind of put all these pieces together.
I have two questions for Amanda and JP. My first question is whether there are any EPA-approved methods to report branched and linear isomers, if that's something that you can get from 1633, or if you have to use a lab-specific method. And then my second question is about analyzing wastewater samples. So the influent tends to have a lot of suspended solids, like Amanda mentioned, which I think is pretty inherent to the matrix itself. So do you all think that centrifuging the sample to analyze it is biasing it in any way, and that you're maybe not getting a representative total concentration when you report the analytes?
Do you mind if I respond?
Oh, yeah,
Is that
go
cool? Yeah, those are great questions. Thank you. I think you're back there, right? Okay, yeah, thank you. So the first question about linear and branched isomers is fantastic. The method I talked about, 1633, reports total, so it does not differentiate. You can differentiate between the two of those. There's a couple ways to do it. There are some standards out there for branched isomers, and so the lab can develop a method, like we could develop our isotope dilution method to quantify for some of those branched isomers based on those standards. There's also a more forensic approach. I was actually talking about this last night with a consultant, where you can look at the chromatograms and you can interpret them looking at the ratios of some of the peaks that you're getting, right? It's not a bad way to do it, depending on what you're looking to use that data for. So does that help? Okay, super. And the second question, I think, was about whether or not centrifuging can somehow present a low bias for samples that present with high solids. That's correct? So that's a great question. Possibly, but we're not really seeing any evidence of that. What we've seen is that centrifuging is probably one of the best ways of managing samples with high solids. We've run a ton of samples, that groundwater that's really turbid or leachate, where the solid phase extraction media just it cannot handle that high level of solids, right? And earlier versions of 1633 didn't allow for centrifuging, and the only thing we could do was dilute the sample, which elevates your limits, and then the data's, what good is it if you're reporting non-detects at a high quantitation limit, right? So the other part of centrifuging is you can actually take the solid phase, right, and perform a methanol extraction on that and include that in your analysis, which we do. And so that kind of gives you an idea of whether or not you're seeing any bias. For the most part, the PFAS tend to stay in the mobile phase. But that's a great question. That answer it? Super.
Hi, I'm an environmental attorney. I actually am heavily involved in the MDL in South Carolina as well, and I could say that Bryan's analysis is really good. It did survive, a similar kind of analysis did survive a challenge, an expert challenge for reliability purposes in the MDL. That challenge is based on it being comprehensive. And part of what the analysis included was a branched linear comparison. And so my question is actually for JP. I'm a lawyer, I'm not a chemist, I call myself a stupid lawyer, not a chemist. And I'd like to really understand how to read those spike graphs, I know that's not the technical term, that you mentioned, to figure out, I don't like relying on other people, I like to understand what these graphs actually say. So is it always the case when you see like a PFOA and you see that initial smaller bump and then the greater spike later, is it always the case when looking at that initial bump suggests that there are branched isomers within that PFOA detection, or is that, faulty?
That's a great question. So lawyers would kill me if they knew I was answering this, right? Because we don't interpret data, we just generate it. But the short answer is no, you can't say that as a rule of thumb. That is always the case. Chromatogram interpretation is challenging. What I would say is, if what you're looking to do is interpret the chromatograms that you could get from a level 4 data package, which, and I agree, I really appreciate you saying that, it's a very powerful tool, is to find a technical expert, maybe a consultant or somebody in the laboratory world to interpret that, right, along with the laboratory data that's been presented. It's a non-answer, I know, sorry.
Thank you.
So I wanted to say thank you to all of your presentations this morning. They've been incredibly useful to the work that I'm doing, so thank you guys for presenting. Dr. Miller, I found your research particularly interesting. So I didn't realize that 1633 was open for interpretation from the actual labs. How do we think that maybe the EPA will create stricter requirements or less room for interpretation? That way we get better data.
We actually presented the same presentation to the EPA who wrote 1633. They thought that with their initial conversation with them, they originally thought that their rules were strict enough to avoid that. But then they were happy to see our data and to see that because of the way that they wrote their method, that it's open and allows for laboratory interpretation. They said they have basically one more go at the apple and one more go at it. So they were, upon receiving our results, they were looking at ways that they could tweak it and make sure that they was more stricter, their requirements. What's ironic is that if you look at the EPA's multi-lab validation study that they conducted independently using laboratories, is that they gave them basically a red tape guidelines in addition to the method saying you can't do this, you can't do that, you can't do this. But what's ironic is that it's not in their 1633 method because it's performance-based, and they thought, when we were talking to the EPA folks, they thought that it was just understood. And now that they saw our data, they're going back and trying to edit it a little bit more and make it more strict. I hope that answers your question.
The question I've got is what kind of interferences do you see in the methods for fluoride in the water? So I've got a facility with a lot of fluoride in it. What do you see there? And I think I'd read at least something on the AOF method being interfered with, but I wasn't sure about 1633 or the others.
Yeah, that's a great question. So is there any fluoride interference? If you've got a sample with high concentration of fluoride, will you have biased data for PFAS? That's what we're looking to root out. So I'm not aware of any interferences you would have from high amounts of fluoride, mainly because of the way that we're looking at the data and the way that we're treating the sample, right? The liquid chromatography mass spec instrument does a really good job of targeting just those compounds with positive ion conformation. So we do see some interferences from certain things, like organics can be interferences. Most of the interferences we see are more on the extraction side of thing, that solid phase extraction portion where we have trouble actually capturing that PFAS onto the media. When it comes to the chromatogram itself, I haven't seen any evidence of fluoride creating an issue, but if anybody has, please speak up, but I haven't seen that. That's a great question.
There's another question back there.
Hi, Jenny. I have a question for the last presenter. What was the components of the project that required you to get that secondary line of evidence with Battelle? Did someone come back and question you, and then that's what led to it? Because I just know that secondary line of evidence is very expensive, and a lot of our projects don't have that budget to do so. So with your initial analysis in fingerprinting, did you think that was enough and the science has evolved so that is enough, or was that Battelle really required?
No, so that was actually my recommendation to the client. So I've worked on litigation projects before, and I was just kind of trying to think down the line. If I'm a consultant and I see this data set, how can I look at it and throw holes in it? And I kind of saw that this was an opportunity where we could collect the samples now, and get the data and see, did it match what we expected or would it be different? And the client also saw the value in that, so we decided to move forward with that testing, just as, you know, another line of evidence in the investigation.
Thank you.
I'm just curious, it sounds like 1633 is much more robust from a QA standpoint, but it is more expensive, right? But you get lower detection limits.
It's the environment. We're not going to burden ourselves with concerns about cost here, Joe. It is more expensive.
I just know a lot of municipalities, DEP's lab still using 537M, but I think federal groups have moved over to 1633. So you're seeing a progression from 537 over to 1633?
On the commercial lab side, we are, and there's a few things driving that. You know, mainly it is a more robust method, and because it is written into more documents, right? We expect it to be more included in the regulatory documents. We think we're going to see a bigger need for it. It is more expensive. Now, part of that is due to the fact that I mentioned earlier that the labs have been running drafted versions of this method, right? And so, kind of important to keep in mind with that is some of those drafts had some pretty restrictive steps in them, right? And those changed throughout the drafts. Those restrictive steps are kind of what drove that cost up. And at the time, the only laboratory accreditation available for a while was through the Department of Defense, which did not allow for any method modification. So, you know, we had, as a laboratory, to follow this kind of one protocol, whereas with the 537 modified or isotope dilution internal method, maybe we could modify some things that would allow the laboratories to streamline the process, providing the same level of quality when it comes to data, but at maybe a faster turnaround time or a lower price point. There was a question earlier about, you know, modifying the method. So the final method that came out does allow for method modifications as long as the laboratories can validate that. And I think what we'll see is that a lot of laboratories will modify the method to optimize for production, right, while also maintaining the goal of a high level of data quality in a way that will allow that price point to come down. And I think the important thing to keep in mind here is that that method will have to be accredited on a state-to-state basis, right? So I expect that these labs will be audited, right, by state auditors, federal auditors, according to that modified method. So I think we will see the price come down in that final method after it's promulgated and states are accrediting.
Perfect. Well, big round of applause to our presenters today. Giving you back 8 minutes for lunch at noon time. So hurry back for the next session, I believe, is at 1:30.